Imagine if a single photon could tell an entire story. If we could capture even the faintest glimmers of light in near darkness.
Today, we are exploring a revolutionary technology that lets us do just that. Welcome to our journey into the world of Single Photon Avalanche Diodes and quantum photography. Did you know that if you have an iPhone 12 or newer, you are already carrying a piece of this cutting-edge technology in your pocket? Inside is a tiny SPAD sensor, short for Single Photon Avalanche Diode, a sensor so sensitive that it detects individual particles of light called photons.
When a photon strikes the sensor, it triggers a burst of electrons, just like an avalanche, creating a strong detectable signal. And what's controlling this process? A diode. Think of it as a one-way valve that only allows current to flow in one direction, ensuring that a signal is properly amplified and ready to be detected. Now you might be thinking, why should we care about fancy new camera tech? But here's the thing, advances like SPAD don't just make pictures prettier. They have the power to save lives through early disease detection, make our cities safer with better navigation in self-driving cars, and even help us respond faster in disaster zones by seeing through smoke or rubble.
Investing in technologies like SPAD isn't about luxury. It's about unlocking smarter, more responsible tools that can improve everyday life in meaningful ways. But before we learn more about how SPAD technology works, its uses, and who's been advancing this technology, let's talk more about how we got here. Because the way we casually take photos today is actually the result of a long history of innovation.
Photography has come a long way from the pinhole projections of ancient China. The 19th century saw the first real photographs, and then came innovations like color photography, smaller cameras, and instant photos. Fast forward to the 21st century, and digital sensors redefined image quality. And now, SPAD technology is pushing the boundaries further by detecting light at its most fundamental level.
That was one of the primary motivations for us to start working on this technology, in that at the rawest, finest level, they capture the best images that physics allows, right? You are capturing every photon, and that is all the visual information that there is.
So, how do SPAD sensors work? Well, unlike traditional CMOS or complementary metal oxide semiconductor sensors that measure photon accumulation in a pixel, which can introduce noise, SPAD sensors, on the other hand, count individual photons with high reliability.
When a photon hits the SPAD sensor, it triggers an avalanche of electrons, multiplying rapidly and creating a burst of current, making it easier to detect. This direct photon counting eliminates noise and unlocks incredible potential. SPAD sensor benefit include ultra sensitivity, less grainy or fuzzy imaging, better capture of quick motion, and a wide range of brightness level.
But at the moment, they face challenges too, requiring complex algorithms, greater computing capacity, and increased costs. However, many players are trying to overcome these challenges. Canon recently commercialized the world's first interchangeable lens SPAD color camera, the MS500. For $25,000 in 2025, it features the world's highest pixel count for color photography, with a higher resolution than Full HD, in large part due to a SPAD sensor the size of your fingernail.
Now imagine taking magical photos with your smartphone from extreme distance, or drones and autonomous car navigating through fog and rain. They are exactly very real and practical applications.
Single Photon Avalanche Diodes, or SPADs, that can perform time-of-flight imaging, recovering depth accurately, and even be utilized to see around a corner.
Also known as non-line-of-sight imaging, where light bounces off surface to map hidden objects.
In terms of applications, again, in a way, sky is the limit here, right? Because if you captured everything, then if you can design the right set of algorithms to extract that information, you can start thinking about really nominal capabilities like vision in the very low light, extreme darkness, high speeds, seeing through occlusions, or scattering, what we call obscuring media.
This technology is even being used to aid in early disease detection through ultrasensitive microscopy, enabling early diagnosis of cancers and other conditions.
Cancer cells removed.
This technology is truly revolutionary. By detecting single photons, these sensors make it possible to capture information that traditional cameras simply can't. The journey of SPAD technology began in academia. At the Swiss Federal Technology Institute of Lausanne, EPFL, where Dr. Eduardo Charbon pioneered this technology. His student, Dr. Kazuhiro Morimoto, achieved the first megapixel SPAD camera, a breakthrough that enabled high-resolution imaging.
On the algorithmic side, at the Wisdom Lab at the University of Wisconsin-Madison, Dr. Mohit Gupta and his team have been advancing computational technique and algorithm to extract valuable information from SPAD data. After completing his groundbreaking thesis at EPFL, Dr. Morimoto brought his expertise to Canon, where he was important in commercializing their SPAD cameras.
Similarly, academics are commercializing their SPAD research. Exploring hardware advances are Dr. Henderson with his startup Singular Photonics, and Pi Imaging, co-founded by Dr. Charbonne and Dr. Bruschini. On the software side, advances are being made by Ubisoft, co-founded by Dr. Gupta and experts from MIT's Media Lab.
None of this progress would be possible without knowledge sharing and collaboration supported by non-profits. For example, the SPAD Science School, co-hosted by non-profits, and the Polytechnic University of Milan, has become a vital hub where professors and the industry share their knowledge on SPAD principles with young researchers and early career professionals.
Key government agencies, like the National Science Foundation, have provided funding for basic research that has played a major role in SPAD development, along with policy frameworks like the International Traffic in Arms Regulations, which regulate its distribution.
At the same time, big private industry players have taken notice and are exploring SPAD sensor application in commercial devices, bringing this powerful technology to the masses.
So when we look at SPAD technology today, it's not just the product of one lab or one company. It's the result of a dynamic, global collaboration across multiple actors from academic, private, nonprofit, and governmental bodies.
And with this powerful collaboration, we are not just witnessing the evolution of imaging technology. We are watching the future of vision unfold before our eyes. And leading researchers believe that this technology can one day replace and improve conventional camera technology, like the ones in our phones, cars, and surveillance system.
As SPAD technology becomes more prevalent, we must consider its impact in privacy and ethics.
There's a bit of a shift that has happened in that increasingly, images are not created by cameras. Images are increasingly created by algorithms. A lot happens between the time light is captured by a camera and when it is eventually consumed by an observer. It starts raising the question of what is reality.
As technology inherits the same rigor, ethical, and regulatory concern as conventional cameras, particularly in surveillance and military applications, emerging use like non-line of sight imaging raise additional security concerns, underscoring the need for specific regulation to address this challenge.
Ultimately, thoughtful policies can help balance innovation with ethical considerations, ensuring a safe and equitable future. And the collaboration of all these stakeholders is essential in driving advances in SPAD sensors and encouraging wide adoption in consumer devices.
As we wrap up, think about this. How might capturing light at its most fundamental level change the way we see the world?
Together, we're not just capturing light, we're capturing the future.